Okay, so this is lecture 27 after a bit of a gap, and today we are going to pick up again on perturbation theory in QFT. We've already explained how to do it in principle from path integrals. So this will be also kind of a revision of what we did. And then we'll go on to explore what the consequences of it are, some of which are quite subtle. So, some time back we derived some formulae under the section perturbation theory for scattering amplitudes, and the key object of interest to us there was the correlation function, which we denote Now, I'll be working today in scalar field theory with one field, but the standard model, as many of you I'm sure know, is not a scalar field theory with one field. It has a scalar doublet, it has fermions, and it has vector Yang-Mills fields, and you have to learn how to generalize these ideas to those cases. And often it happens that we just do this and we stop. But in this course, at least, I would certainly like to talk about how we do this with vector fields and maybe even spinor fields, but though we have limited time. So we are only starting with this. There could also be a theory, for example, with multiple different scalar fields. There need not even be a symmetry between them. So supposing I have a theory with phi 1, phi 2 and phi 3 and all different potentials, and I want to calculate, say, phi 1, phi 2, phi 2, phi 3 or something like that. I could just do that. So all of these rules need to be generalized, and I'm counting on you to make some of those generalizations in your own head or try to work them out. Okay, and when we need to specify the theory, we'll take phi 4 theory, but right now, first thing I want to say is that this is the object of interest, and since this phi that appears here is really our friend the fluctuation eta. I won't always write it that way, but you know, often we work in a theory that's not even spontaneously broken, so then phi is eta. If we work in a theory where the symmetry is spontaneously broken, we shift phi to, say, a plus eta, and then we rename eta as phi afterwards for doing calculations. So this phi always means the fluctuation. That's the only thing whose correlation we ever calculate. And clearly the 1 point function phi of x1 is 0, because that's the whole point of the fluctuation. We chose it so that the vacuum expectation value, if any, is in the classical part, so eta shouldn't have any. So therefore this is clearly 0. So we start with the 2 point function. So today we'll talk a little bit about the 2 point function phi of x1, phi of x2, and also the 4 point function and the reason to stick to these two is that we are going to work with the Lagrangian of phi 4 theory, and that doesn't have a 3 point function. You can work it out, and you'll see from what I'm going to do now that there's no way to get a 3 point function. There's no way to get any odd point function, in fact. And you can directly trace that to the symmetry of this theory, a discrete symmetry under phi goes to minus phi. So if there's such a symmetry, then there can't be a 3 point function, because the whole 3 point function under that symmetry would go to minus itself and it would be the same. So therefore it can only be 0 and all odd point. So we are going to focus on 2 and 4. Okay, good. Now, what do we want to say about these cases? Well, we've already said some things. I'll just quickly review them and then get to the interesting parts of the calculation. So, the key result which we derived earlier was Wick's theorem, maybe we didn't derive it, but I give you an example. And in path integral language, it's extremely simple to apply this theorem to get perturbation theory. So the theorem itself simply says that every endpoint function breaks up in a free theory, breaks up into a product of 2-point functions, okay, in all possible ways. So for example, in the free theory, that means without this potential, then this 4-point function would be phi 1, phi 2 with phi 3, phi 4, two 2-point functions, and then 1, 3, 2, 4, and 1, 4, 2, 3, and you just add them, yes.
Are we working with lambda by 4 or lambda by 4 factorial?
I now like lambda by 4 for some reason. It's not absolutely crucial. No, in my notes I have 4 factorial. Thank you. I'll stick with 4 factorial. I'm never sure which one is better. Okay. Good. So Wick's theorem we know. And okay, maybe I'll just write it schematically anyway, just so that you. So now I'm assuming that we have even number of points in my correlation function, and also I'm assuming it's in the free theory. Free and quadratic mean the same thing, and it means there cannot be any higher than quadratic term in the Lagrangian. Let's be very, very clear about that. So this is equal to product I not equal to j, probably I less than j is better, phi of xi, phi of xj over all distinct pairs, and then the sum. Sorry, this is not what I wanted to write. It's a product of such pairs. Okay, I think writing it this way I'll have to use permutations, and I don't want to do that, and I also don't have any eraser today. Here it is. Okay, let's just write it out in longhand. Okay, so each phi of xi appears once and only once in the product, and it will appear with another phi, which can be at any of the locations, and each such pair will occur once. Okay, and then the all permutations means not counting that that particular arrangement again. So all possible ways of breaking up 2n, the numbers 1 up to 2n into pairs. Okay, good. Now what did we learn about? So this is this, and this expresses the free n-point function in terms of the free 2-point function. So all these 2-point functions are the free 2-point functions. So if we know the free 2-point function, then we know all n-point functions in a free theory, and we actually know more than that. So for that we need to work out what is phi of x1, phi of x2 in a free theory. And for the scalar field, I worked it out some lectures ago, and it's exactly the same. So for 2 points, I like to call them x and x prime. And it's exactly the inverse of the quadratic operator O as a function of x and x prime. And this is the same as what we call the Feynman propagator, x minus x prime, for scalar field. Which is equal to I integral d for p over 2 pi to the 4th e to the minus I p dot x minus x prime over p squared minus m squared plus I epsilon. And there's a similar expression for fermions, but it has some gamma matrix contracted with p in the numerator, and it's in the notes, and we've already discussed it before. Okay, so this is the 2-point function, and it's obvious that this is the inverse of the operator O, because the operator O is box plus m squared, and if you act with box plus m squared here, you can take it inside. Box gives me minus p squared, and then you have minus m, box plus m squared. So box gives me minus p squared, then plus m squared, then that cancels this up to a sign, and I get delta. So box x plus m squared df x minus x prime should be equal to delta for x minus x prime. This is what inverse means. This is O. Okay, good. So I simply put that expression in every term here and I can get the endpoint function for any free theory. But now I want to go to interacting theories. And for interacting theories, okay, I forgot also to write one more thing, which is recall the definition of this correlation function. In general, in path integral language, it's defined as the, so again I'm using phi in place of eta. And here we did this calculation quite carefully. You just have to insert a lot of classical functions phi inside this integral and then divide by the same thing without those insertions. Okay, so this is the definition of the correlation function, and then this is what I want to calculate, and and now we can ask the question, well, what if the theory is not free? So far we've solved the problem for the free theory. And what we argued then is that if the theory is not free, then we get an expansion in powers of the interaction. And so I wrote down for you a formula which I'm looking for. I'm not finding. Give me a minute. Where did it go? Good. So the first thing we can do using the path integral is to generalize this free expression to the interacting expression for the 2-point function and then move on to higher ones. And for the 2-point function, we have phi of x prime interacting is equal to, so it's actually equal to that with n equals 2, right? So now we can manipulate that by saying that it's equal to phi x1, phi x prime free plus, so what's the difference between free and interacting theory? S has a term minus lambda by 4 phi to the 4th integrated. That's the difference. So I get a term proportional to that. So actually, I think in my notes I have made some normalization errors here, which I should be a little careful about. So, not liking this. So you see, this is clearly true, but if we want the whole thing normalized, then we have to expand the numerator and denominator of this, and then divide them, and then carry out that division in perturbation theory order by order in lambda. It's quite a tedious process. Unfortunately for that I need some new notation. So let's try this one. We'll call this double bracket correlator phi x1 up to phi xn divided by double bracket 1. Double bracket simply means you, whatever this thing is, you put it in the path integral, but you don't divide by anything. Okay, so this double bracket is just the numerator of this expression, and this is the denominator. Okay, so in this way of writing things, the normalization is done explicitly by dividing by the denominator. So for example, if the numerator had no fields, then this would also be double bracket of 1. So would this, and they would cancel, and we would find that the normalized correlator of identity is just 1. But the unnormalized one is some horrible thing which we have encountered early in the course, something which is likely to be divergent and so on. So it's very difficult to make sense of this and this separately, but we normally work with ratios, which make sense. Okay, if I do it in that language, then it's much easier, because now this is equal to phi of x prime int divided by 1 int, and each of these has a perturbation series in the 5/4 interaction. So let's write out the perturbation series for phi of x prime. So that consists of this numerator with n equals 2, so phi of x and phi of x prime here, and s has the free terms and the interacting terms. So it's path integral d phi e to the I integral d for x L free plus L interaction, and then phi of x prime. Okay, and L interaction is just minus lambda by 4 phi to the 4th. Okay, so now I'm simply going to take L interaction, which is of order lambda, which is my coupling constant, and take the exponential of it and bring it down once, twice, 3 times to generate perturbation theory. If you remember how you did this in QFT1, I'm presuming you did it in QFT1, the process was a bit different and involved going to the interaction picture and working with the Hamiltonian and so on. But in path integrals, Hamiltonian is abolished from the story. It can be used, but it's not normally. And we don't need to do anything artificial. The Lagrangian comes to us with a free part and an interacting part. It's very unambiguous which one is which. The quadratic one is free, everything else is interacting. So it's very clear that the interacting one needs to have a parameter. In the multi-field case, it could have many parameters, and then we need to bring those down and count orders of the parameter as orders of perturbation theory. So obviously the first order, so everything is inside d phi, and the first term is just this, which can be called phi x prime free. So obviously the leading term in the interacting 2-point function is the free 2-point function. But there are more terms. So the next term is minus I lambda over 4 factorial. Now I have a path integral d phi. I have e to the I s free, which is always there. And downstairs I have phi x prime and integral d for y, 5/4 of y. And in the next order, I have to remember there's a half from expanding the exponent. E to the I L comes down twice, but there's a 1/2 factorial, so that's this. Then there's the coefficient in L interaction twice. There's a single path integral always. There's always e to the I s free. There are always these fields. But now there are two integrals in y, independent ones. And this is how it goes on. Okay, because we brought down the term integral d for y, 5/4 of y, twice. So when we do that, each 5/4 has an argument, different argument, and each one has to be separately integrated over all of space. Okay. I'm not sure if this is something you already know very well, or it's something that, it's not challenging at all, right? Good. Okay, so now we have to work out the consequence. Now this is the numerator. The same thing can be done with 1, which is the denominator, 1 interacting. Everything is the same except this phi and phi prime are missing, but there are still some calculations to be done because we are still pulling down 5 fourth, once, twice, 3 times and so on. So that's it. Then we divide one by the other. Good. I probably have to improve my notes a little bit before I put them up. Okay. So that's done, and now let's actually do the calculation and see what we can learn about it. So supposing we work with 5/4 theory, okay, I should have said. So once we have such an expression, for example, first order, I have 1 phi, another phi, and 4 more phi's. So there are 6 altogether. Okay, 4 of which are at the same point. And now I have to use Wick's theorem to contract, as they say, a phi from any of these 2 phi's together and any other 2 and any other 2 and sum over always. And then now notice that everything is in the free theory. So now the 2-point function that Wick's theorem breaks this into will be df, the familiar 2-point function. Okay, that's the good part. So now once we have done this expansion, we can forget about the interaction. It's already taken care of, and every calculation is done in the free theory. This is what perturbation theory really is. It's doing calculations in a free theory by treating the interactions as a perturbation. The price you pay is, of course, you have to do many orders of calculation. Okay, so now let's see the example of how this actually works in the 5/4 theory. And the best way to do that is to draw a diagram and write what it corresponds to. So I mark x, I mark x prime, I join them by a line. This is the free term. Okay, so this is this. This is just a representation of that, and all lines will be this, which in turn is equal to df, as I've told you, the Feynman propagator. Then I have to add minus I lambda over 4 factorial, and now I have to take 6 points, x, x prime, and 4 coincident points y. 1 line comes out of each of these, 4 lines come out of these, and I have to join them in all possible ways. Put a df for every line and then integrate over y, over all space. So for example, one of the options is I join these two, and these two. This is one possibility, yes.
If we have the bubbles, then that should be double
Double.
brackets. Right?
That's also
Sorry. Good. Thank you. That's exactly right. Okay. So exactly. So right now we are doing the expansion of the numerator. We'll also do the expansion of the denominator, and then we'll find a trick which allows us to directly find the expansion for the not doubled bracket, the normalized one, which is the one we really want. So this is one diagram at this order, but there's another diagram where I connect one x to a y, the other x to a y, and then connect the two y's. So it's this. With x, x prime, and y. What you should do to verify that your diagrams are making sense is there should be one point for every field that we have inserted in the problem in our correlator, okay? And that point should only have one field coming out, one line coming out of it, because it's an external field, okay? But then there are what we might call internal fields which came from pulling down the interaction. They were not put by us, they came from the Lagrangian, okay? So those have, from each point, there has to be that number of fields which are in the interaction. So 5/4, there have to be 4 lines coming out. And so this is it. And now the problem is twofold. So now we have to associate with each of these lines a df, and we also have to count how many ways each diagram comes. So there's a combinatoric factor which I'll write here. Now in this course I simply don't have the time, and I think it's a very straightforward exercise to learn combinatoric factors, so I'm going to ask you to do that on your own. Plus I assume you have done it in QFT1. You've done combinatoric factors, okay? So that's the easy part, but for the rest of it, we can simply take this and say, well, this line is df x minus x prime, that line is df y minus y, and the lower line, this line, is also df y minus y. So we have 3 df's, which is correct for a 6-point function. And why do we have a 6-point function? Because 1, 2 plus 4, 6 fields. Okay, and this one has a different combination, df x minus y, df x prime minus y, df y minus y. Now y minus y is of course 0. That's this one. And similarly here we have df of 0 whole squared. Now we see some interesting disasters befalling us. First of all, this has to be integrated in d for y, but nothing depends on y in here. So this is going to give me an infinite factor proportional to the volume of all space-time. This one also has to be integrated. It's a little better because at least these two things depend on y, but there's still df of 0, and df of 0 by itself is divergent because it is the integral d for p over 2 pi to the 4th I upon p squared minus m squared plus I epsilon. And you can clearly see there's no phase because it's argument 0. If there was an argument, there would be a phase. If there was a phase e to the minus I p dot x minus x prime, then we might hope that the integral still makes sense. But if there's no phase, then we can just see the growth of this for large p. This goes like p to the 4th, this goes like p squared. So at infinity, for very large momenta, this isn't going to converge. And so this is already a divergent object. So a lot of problems right from the beginning before we actually try to extract any physics from it. Okay. Now a nice feature is that what happens if we expand the denominator, so that we can do in parallel. This is this and this is 1. So we can do the same diagrams. What's missing is x and x prime. Y is still there. So in the lowest order, there's just 1. Okay, because in lowest order there are no x or x prime and there's no y also. The next order term is 1 minus I lambda by 4 factorial, then combinatorial factors. And I have one y and it has to be contracted with itself, so it forms this kind of thing, which is df of 0 squared. Okay, so note that from the denominator also we got this bubble diagram, as it's called, which is the same as this times that. Okay, and this pattern persists. That is, whenever the numerator has a diagram where there's a bubble disconnected from the x and x prime, then the denominator has the same type of bubble. That's almost obvious. Okay, so now if we divide the two and do things carefully in perturbation theory, we'll see that the contribution of this cancels. After dividing by 1. And it's not just the contribution of this particular bubble, but all bubbles. I worked it out in my notes precisely. I think it's something that you'll learn best if you work it out for yourself. You simply work out the perturbation series for the numerator and denominator, and you'll find that the contribution of this bubble cancels the contribution of this bubble, and therefore we can forget, and this is true at higher orders also. Okay, in higher orders I'll have 2 points, y1 and y2, and from this 1 expanding 1 I'll get diagrams like, for example, this. Okay, I'll also get diagrams like this, just 2 copies of the previous one. All look like bubbles. There cannot be anything except bubbles when I expand 1 because there were no external points in 1. Okay, but the numerator will always have such terms accompanied by the free propagator from x to x prime. And so the ratio of the numerator to the denominator for the bubble diagrams, we just have to keep the x to x prime and drop all bubbles. But what won't cancel is this diagram. This has no counterpart in 1. 1 cannot produce a diagram like this because a diagram like this needs 2 external legs. Otherwise, there's no such diagram. So we keep this, we drop that. So that's the rule. Let's make it into a formal rule. So phi of x1, phi of x2 interacting, which is equal to double bracket phi of x1, phi of x2 interacting divided by 1 interacting is actually equal to phi x1, phi of x2. Well, I shouldn't even do that. I should just draw them. Oh, sorry, these are x and x prime. So this is equal to this x and x prime. Then at next order, we have this. What will we have at next order? So here's x, x prime and y. So you see, in this quantity, I don't have to put the bubble at all. I just forget about it, and in the same breath, I forget about the denominator. Not only the denominator takes away the unwanted diagrams, it also takes away itself in the process. So there's much less to calculate because of the taking this ratio. So the next diagram, for example, could have a term like this. There have to be 2 y's, remember. But it could also have a term like this. This is not a bubble because it's connected to the x prime line. Anything which is connected through a series of lines to the external points cannot be part of a bubble. Okay, and there can still be more diagrams. Actually, you would really enjoy if you sit down and try without looking at any reference. Just try to draw all possible Feynman diagrams. So here's another one, y1, y2. And for each of these, you can immediately write down what is the contribution as a product of DFs, each of which is a free Feynman propagator. Yes?
So here we are taking a ratio of phi x in the double bracket in interaction with the identity.
Yes. It's done. The ratio taking is done, and the rule is that this is the answer.
So what do you mean by cancelling? Like, do we expand the denominator as a perturbation?
Yes, yes, we expand the denominator. So for example, if denominator is 1 over 1 plus x, then I bring it upstairs as 1 minus x, because its denominator is, each one is expanded to a fixed order in lambda. And when I have for example, supposing I have something of the form a1 plus a2 lambda plus a3 lambda squared, and downstairs I have b1 plus b2 lambda plus b3 lambda squared. This ratio can only be trusted to order lambda squared. And how do I find it? Well, I keep the numerator. This is very, very important, and I'm so glad you asked it, because people make a lot of mistakes with this. So the first step is completely trivial. I just bring this up by putting a minus 1 on it. Okay? Okay, now what do I do? Well, I keep writing the first factor. But the second factor, I factor out the leading term B1, inverse. B1 comes out, there's an inverse. And inside I have 1 plus B2 over B1 lambda plus B3 over B1 lambda squared. Now there's always a plus dot dot dot, but I've decided to truncate my perturbation series at second order. Okay, now I make an expansion of this. What is the expansion of this? 1 minus B2 by B1 lambda, right? This is 1 plus x to the minus 1. So it's 1 minus x plus x squared. Okay, now this is 1 minus x, but this term is also there in minus x because the whole of this, everything other than 1 is x. So this is there. But then in x squared, I have to square this whole thing. But when I square it, I'm only allowed to keep the square of this term, and I cannot keep either the cross term or the square of this term, which would be of higher order in lambda, higher than square order. So plus B2 by B1, B2 by B1 whole squared lambda squared. This is it. This is the inverse of this in perturbation theory to second order. Now I multiply these two and keep up to lambda squared. And I should be careful, one second, not to lose terms and also not to keep terms that I'm not supposed to keep. So lambda squared times this lambda squared, certainly I'm not going to keep. On the other hand, if I look at order lambda, the contribution is A2 times 1 and also A1 times minus B2 by B1. So I have to combine them. At order lambda squared, there will be this times this, as well as this times that, as well as that times this. I have to keep all of them. So you should always take a bracket lambda to some power and then add all the terms that contribute. And this is the statement about what cancels. This is worked out in the notes quite in some detail for the cancellation of one bubble diagram. So that you'll find there. And you can, from that, you'll be able to see how it's done. But thank you for bringing this. This is clear, I hope. This is just pure algebra. But it's very important because people, when asked to calculate numerically, almost inevitably make a mistake in taking perturbation series to an order higher than you're allowed. Why are you not allowed to keep the next term in this? Because we don't know these two terms. We only know them up to lambda squared, and we have an error of order lambda cubed which we never calculated. Therefore, there's an unknown error of order lambda cubed. Therefore, if I take this to order lambda cubed, I'm adding the lambda cubed term which I calculate to an unknown error. If I add it to an unknown error, the answer is meaningless. I'm confusing myself thinking that I know something in order lambda cubed when I really don't know it because I lost the information from the beginning. This is a very key feature of all perturbation theory. So once you've got that, I think you're familiar with it, but I think it doesn't hurt to repeat it. So this is it, yeah. So this settles, Sarthak, your question about this calculation. Good. Okay, so all kinds of diagrams like this, and all of these have to be calculated. Yes?
Sir, when you do that expansion, you have this lambda plus lambda square and all of that. So you're doing 1 plus x inverse, right? And then you're saying that is like 1 minus x plus x square, all of that.
Well, 1 plus x inverse is just 1, depends what you mean by x. So if you're here, so this is 1, this is x.
So it's always the truncation that is x, right? You're not calling the entire sum x.
I could call everything x. In my mind, it's the entire sum. But the point is that all I'm allowed to keep of that is the terms up to order lambda squared. So
but
it makes.
We don't know whether the sum x is, like, we cannot assume that the sum x is not of order 1, right?
No. We are working in perturbation theory. Perturbation theory means an expansion around lambda equals 0. So x cannot be of order 1. But so, well, you know what's a Taylor expansion, right?
Like one example is like a simple sum 1 plus half plus 1/4.
Yes.
If we consider half plus 1/4, all of that,
Yes.
the sum is still of order 1.
Yes, but that's because you're doing 1 plus half plus 1/4. If you were doing 1 plus lambda by 2 plus lambda squared by 4 and so on, then for lambda arbitrarily small, that sum cannot be of order 1. And the whole point is that you have to treat lambda as arbitrarily small, as they say, parametrically small. It's only, you can put the number after you finished your calculation, but when you have a small quantity in which you're expanding, you have to say in your mind that this is an arbitrarily small quantity, but I get to decide whether that means that lambda squared itself is treated as 0 or lambda cubed is treated as 0 or which order. That depends on my strength. If I know how to calculate to 6 orders, then lambda to the 6th I can calculate, and from 7th onwards I treat that power as 0. It's my choice. But I must make that choice before I start. I can't make the choice halfway in my calculation. And from this you see that I have made the choice for the numerator and denominator which I calculated separately, to stop at lambda squared and not calculate the next term. Once I made that choice, I have to only give you this answer. Okay. Now it could be that lambda is really such a value that this sum doesn't even converge, in which case all I can say is my perturbation theory is not applicable. So you should never assume that your perturbation theory will be applicable. But when you want to do perturbation theory, these are the rules. Then the rules may give you a meaningless answer if you're unlucky that your sum never converged in the first place.
So, in
Yeah.
order to understand like what lambda is small enough,
Yes.
can we say that starting from the B2 lambda till all higher terms,
Yeah.
that summation should be less than the radius of convergence of 1 plus x to the power of minus?
Certainly. I mean, but that's that's essentially the same statement as saying that this converges, right?
Right. Huh.
For arbitrarily small lambda. So yes, I mean, however you want to put it, the main thing is that we simply fix an order and we expand to that order. Okay, so at some point when we fix an order, we are actually throwing out the question of convergence. There's no longer an issue of convergence because I have simply stopped calculating at this point. So there's nothing to converge. The question you may ask is, well, there's a true field theory and a true path integral which some genius can calculate without using perturbation theory. How well does my answer agree with that genius's calculation? But internal to your calculation, there are not many rules to calculate. There's only one rule: truncate and calculate. You're not supposed to worry about the radius of convergence. You can come back and say, yes, I want to evaluate the sense of this perturbation theory by estimating the growth of A2, A3, A4. There are people who do that. That is called Borel summability, and there's an entire beautiful subject of QFT which studies convergence and non-convergence of such series and how you can even improve them. But we can't learn to improve them till we learn how to do the basic perturbation theory. And surprisingly, in some theories like quantum electrodynamics, this works fantastically even up to 6th, 7th, 8th order. So it's worth learning. Okay, good. So now with all this, we've learnt one thing, which is that disconnected diagrams are gone. Where disconnected means bubbles which don't connect with external lines. Okay. Now when we consider 4-point functions, we'll find there's a new type of disconnection which is a little different, and it isn't gone. So let's consider the 4-point thing. Maybe I can just do it here. I just put this and it's pretty straightforward. And now my series will have 4 external points, so I'll mark them: x1, x2, x3, x4. And now I have to draw all possible diagrams in the perturbative expansion of this numerator and denominator. Now the theorem I told you that the denominator cancels bubbles in the... Well, before we get to bubbles, let's first ask what happens at lowest order. By the way, lowest order in field theory is called tree level. You know that, I suppose. So at lowest order, there's no y. We have not expanded the interaction term. So what can I do? Well, Wick's theorem says connect this way, or connect this way, or connect this way. I'm not going to keep writing the external x's, but they are all, whatever order I wrote them in is fixed for all diagrams. Don't ever change the external points in any one diagram relative to another one. So this is it. By the way, in my notes, I wasn't able to do this funny thing. So my lines look like this, but I put a heavy dot here and no heavy dot here, that means they don't actually intersect, they just cross each other. There's no actual vertex here. This is lowest order. So when you see a crossing like this, you're supposed to interpret that way. So there are three terms. Okay. What will interactions do? Well, they'll add one y, and there are many ways I can add a y. One of them is to put the y somewhere outside and I have a bubble, but we've just learned that this is not going to contribute because this is going to cancel its effect. So these I'll never draw. This is my rule that for connected diagrams, I never draw I never worry about the denominator and I never draw bubbles. So every y has to be sitting on one of these legs. So what can I do? Well, here's an example. The y is sitting on this leg and not on this, because there's only one y, I can't put it on both legs. This is order lambda. The presence of a single y means I'm in order lambda. Okay, then I could also put it on the other leg, same order, and it's a different diagram because here it's on the leg between x1 and x3 and here it's on the leg between x2 and x4. Then I can do the same here, it's quite boring. And I can do the same here. Okay. Now if you stare at this long enough, you'll get a sort of sinking feeling that nothing is happening. If this is supposed to be a particle physics experiment, then some particles are coming into the experiment and going out, or maybe they're coming in here and going out here. I don't know who's coming in and who's going out, but what I know is that the particle that's traversing this is never meeting this one. Okay, here it's coming in here, going out here, and never meeting this one. But here it's also the same. This particle is coming, it's doing some self-interaction and going out, but it's still never meeting that. So should we call these connected or disconnected? So these are disconnected in a new sense. There are no bubbles, but they are disconnected in the sense that the particles or the fields don't meet each other. None of these diagrams. So is there any hope? Is there a diagram where they do meet each other? Yes, there's only one with the same labeling of these 4 points. This is the diagram with now a dot here, and this is y. This is the diagram where actually all the 4 points meet, and we have some hope of getting physics out of it. Physics will come because in some interpretation these two particles will scatter at this point with strength lambda and then go out, and this point can be any point in the entire universe. Of course, the probability will depend on where I am because all these propagators go from the point to y. So obviously if y is on the moon, it's not going to contribute, but we have to still integrate over all d for y. So we have to formally sum, and the probabilities take care of themselves. That's how the whole thing is set up. So this is the only good diagram, and those are all very bad, but I haven't got rid of them. So what am I supposed to say at this point? I haven't got rid of them because this division is already done, and that's the answer. So it's this plus this plus this plus all of these plus all of these plus this, but this has a special status. Okay, so I don't even remember what's the right word to use, but the important thing is, and this I'll write, but I may not go into detail, going from correlation function to the scattering matrix, S matrix, and from there to the cross section. These are measurable quantities, is a complicated process. But the important thing about this process is, in this process we drop all well, I don't know what to call them. There should be a good word and it's not coming to my mind. We drop all those diagrams there. All diagrams. Maybe I can call them reducible. I'll see if there's some better word, I don't remember. All reducible diagrams of this type, where two sets of particles don't interact with each other. Is that point clear? Yes.
So just the diagram and the bottom right,
Yes.
the loop should be on the other line. Right?
Yeah, absolutely. I just drew the same diagram first. What I had drawn was the same as this. Thank you. Yeah. Okay. So now this is not the, I said it's a complicated process to go from correlation function to S matrix. One feature of that complicated process is dropping all such diagrams. That's not the that makes our life easier actually. Okay. The other feature is choosing who is incoming, who is outgoing, whose energy is positive, whose energy is negative, going to momentum space, all these things. And it takes a few steps to get there. Again, you might have done those steps. I don't know how well you remember them, if you have indeed done them. But right in the S matrix, there's an unambiguous interpretation of which particles are incoming, which are outgoing. Okay, and here there isn't. In correlation functions, there's nothing like incoming and outgoing. So it's only in preparation for the S matrix that we decide to drop those kind of diagrams. And this, if we stick to diagrams like this, where all the four particles meet at least in one place, then we'll have prepared the contribution of the correlation function, which will be used to get the S matrix. I could give it another name, but that's not important. The important thing is that this, for after all this, the first order diagram is this. Okay, and the zeroth order without any, and this is of order lambda, and without lambda there are no diagrams, because in fact these diagrams are of order lambda to the 0, but none of them contributes to the S matrix. Okay, again I misspoke. The S matrix is written as a kind of identity matrix plus a T matrix. It's really the T matrix that these don't contribute to. So it's the one part. The one part means scattering without any interaction. In any scattering process, there's always a chance that these particles will miss these particles completely and just go out. Well, we learn nothing from that, so we might as well not measure it and not calculate it. That's the thinking. That's why scattering cross section is a quantity with dimension of area, which tells you the effective area that the incoming particles hit when they scattered. And obviously that tells you something about actual interaction. And that's what is directly measured. Good. Okay, I can take 5 minutes more to make another point, which is quite interesting. Well, 2 points. One is, of course, the fact that we should go to momentum space. This is as much as we should do in position space. And what we need to do is to Fourier transform. So we should take this thing, and I'll work with the 4-point function. Well, maybe I can work with the endpoint function. So let me write some definitions and then I'll stop. So first, we'll define d tilde Feynman to be the momentum space propagator. By definition, it's that thing whose Fourier transform is the one that I wrote for you previously, and this is obviously the Fourier transform of the df in position space by construction. In fact, it's easier in momentum space. This is the first reason why momentum space is so good. Good. Now, let's look at an example of, for example, this diagram, the one I erased with a y and 4 x's. So this diagram is product of df of xi minus y as I goes from 1 to 4. That's each of these 4 lines. Okay, and then I'm supposed to integrate it in d for y, and I have to put minus I lambda over 4 factorial times combinatorial factors, which turn out to be 4 factorial. So this is actually the correct answer. And this thing I can write using the definition of df as minus I lambda d for y product I equals 1 to 4. So each df is given by an integral over ki over 2 pi to the 4th I upon ki squared minus m squared plus I epsilon. So I put all the df's in, and finally I have e to the minus I summation I ki dot x I minus y. Okay, so I've just put in all the d's. Yeah, you have a class or an extra class? Huh? Quiz. What quiz? Astronomy. Okay. I should stop in that case. Okay, this is all I wanted to say. Then now after putting this in, we see that the y integral can be done, because the y integral is e to the minus I summation ki dot y, and it gives me delta 4 of summation I ki, maybe with a 2 pi to the 4th. Okay, so finally I can write my expression as minus I lambda. So now the y integral is done. And then I have product over I from 1 to 4 integral d for ki over 2 pi to the 4th I over ki squared minus m squared. Very often we will not stop writing this I epsilon, and then we have 2 pi to the 4th delta 4 of summation ki, and that's the whole thing. No, that's not the whole thing. There's also e to the minus I ki dot xi. Okay, so yes,
Summation ki.
summation ki is understood. Okay, I should put it. Good. Okay, and what I'll simply do is define this part of it. I'll collect this much and this much, and I'll call that G. So I'll just, and that's where I'll stop also. So the Fourier transformed 4-point function, 4-point correlation function, I'll define as G tilde for Fourier transform k1 up to k4 is equal to minus I lambda product I equals 1 to 4 1 over I over k squared minus m squared plus I epsilon, and with that we are done, because you see that the position space correlation function, which is this, is of the form this times that which is G and Fourier transform. So another way of saying it is that this thing is the Fourier transform of the original 4-point function. Okay, only one little thing is that this isn't really the Fourier transform, it's this times the delta function which is the Fourier transform. So when we look at momentum space correlators, we always drop the delta function by hand, but it's always there, we just don't write it. And therefore this quantity should only be considered when k4 is equal to minus k1 minus k2 minus k3, because it's multiplying a delta function which conserves momentum. Good. Okay, we'll pursue this in the next lecture, and try to look at diagrams of higher order than this one, and then start to deal with the issue, what about how do we calculate those, which are called loop diagrams, and that will lead us to the problem of renormalization.
Sir,
Questions? Yes, please.
these new type of disconnected diagrams, do they contribute in the one part or the T part of S?
They contribute in the one part. Exactly. That's why we drop everything except what contributes in the T part. That's the key idea. So actually we had a very complicated looking perturbation series with a numerator, denominator, bubbles, and then these kind of non-interacting contributions, but all of them go away, and we are restricted to, in first order, only this diagram, and in next order, two such y's, but all the x's have to be connected to them somehow. None of the x's can propagate back to infinity on its own without meeting the rest of the diagram. And it's easy to state the rule in words, and it's a nice rule because that captures the physics of the process. It's also the thing that we really can calculate. So we can focus on the thing that's worth calculating.
So
Yeah.
is that also the reason why we can drop all the 4 factorials and keep
No,
only
we-
I lambda? Because
Yeah.
if we had
Yeah.
if we had these sort of diagrams,
Yeah.
the combinatorics of that won't be exactly 4 factorial.
No, absolutely. But only this diagram cancels the 4 factorial. The next order diagram won't cancel the 4 factorial squared. In the next diagram, there'll be half and there'll be 1 by 4 factorial squared. And the combinatorics is not going to cancel all those
Then
factors.
when we write the Feynman
We have to
rule,
calculate them. Feynman rules always say calculate the combinatoric factors.
like in momentum space, we always say that the vertex will have a minus 1 by minus I by lambda. Like that
Minus I lambda, no, minus I lambda by 4 factorial. At least in my Feynman rules, the vertex has always got minus I lambda by 4 factorial. And then I manually count how many diagrams there are. I find that easier. Other people say no, only put minus I lambda and then put some factors to compensate for over cancelling those factors, and that I find very roundabout way to do things. If you want, I can spend some time next time showing you my way of calculating combinatorial factors. I like it.